Hey, hello there. Today's Leetcoding challenge question is called prison cells after n days. We have a prison with 8 prison cells in a row. Each cell can be either occupied or vacant. And in the code, it's given to us as a list of integers. So we will have a list of 8 numbers. Each one will be in 0 or 1. 1 means that the cell is occupied. 0 means that the cell is vacant. So every single day, the state of the prison, it means that the 8 values in the prison row is going to be updated according to this following rule here. So for any cell, if we want to look at the state for it on the next day, we look at the 2 adjacent neighborhoods. If they are both occupied or vacant, the cell become occupied. Otherwise, it will become vacant. This otherwise catches all other cases. So it also catches this boundary case here. Since that the prison is a single row, the leftmost and rightmost cells, they don't have 2 adjacent neighbors. They only have 1. So they fall into this second category. So from day 2 and on, the 2 leftmost and rightmost cells must be vacant. So their values has to be 0 all the way. So the question is given us the initial state of the prison. We want to return the state of the prison after n days. So if we just code this rule here, and we can run this function to get the next day state for the prison. This would take a linear time to do this get next day, and we just run that for n days. It will be an okay solution. It's just going to be slow for large size of n's as input. We'll do a little bit of analysis also. So this is its first example. We have the prison cells, 8 different values. It's doing 7 times of the get next operation. So the total runtime for this is 7 multiplied by 8, I guess. So it's the get next is basically linear with respect to the prison size, and you run it for how many n's you have in this small case. In the large case where n is really huge, we really don't want to run this brute forcefully. The reason being that if you look at the prison here, we know that the leftmost and rightmost has to be 0 all the way after day 2, since day 2. The only thing that can change is the middle 6. So since that they take value 0 and 1, there are only 2 to the power of 6 total possibilities. So it's 64. So when n is large, much larger than 64, there are going to be repeatable patterns of the prison. So the reason being that there are only 64 possibilities, and you're looking at an n that's really large. Once the prison run out of 64 possibilities, it's going to repeat itself. So once it's repeating itself, the subsequent next day, it's going to be repeating from the prior thing. So it's going to be a loop, repeatable loop there. So instead of running this n times, we will look out for when the loop starts and how long that lasts. And for the remainder number of days, we're just going to look at how many complete loops it can run, and just subtract all those days directly out, and look at the remainder a few number of days and just run the get next day for that remainder number of times. So for that reason, we want to identify loop and maybe shorten the n when n is large. So to identify the loop, we will need something like this to store the day when we see the state of the prison, so that the next time that we see the same state, we're just going to take the date difference. It will tell us how long the loop will last. So that's the big idea. So let's code this thing up. So we're gonna do is to use a map to hash table to store the day that we see the state of the prison. And then we're just gonna try to do this loop running the get next. So the first thing we do is to check the current state. If the state is in the mem, we have seen this state already. We want to break and deal with that. Otherwise, we will try to do 3 things. One is to decrement n, and then update the state. Before that, we would just memorize the current state, associate the state with the date when we see it. If the loop never breaks, that means n is relatively small. We haven't identified a loop yet, but we already done n times the simulation, the get next, so we return the state. Return the last state. Otherwise, we will just do a modular to complete the number of complete cycle we can do, and only do this get next for the remainder number of times. So it will be the length of the loop will be the n at the breakpoint, and the last time you see the state. So it's going to be memo state subtract n. So the difference in the brackets are the length of the loop. Do a modular is going to be let's just say that you complete the maximum number of complete loop you can do. What's the remainder number of days? And we're just going to run the get next for that many times. So actually, if n is 0 after the while loop, this will be 0. So the state won't run. So I don't need this return, right? Okay, so this is nicer. Okay, let's code the get next. So you know that from date after the initial date, the two boundaries are going to be 0. The only thing remain here is the middle. So we are comparing 0 with 2, 1 with 3, 3 with 5. So they are 2 apart. So we zip the same state 2 positions apart and do the comparison. The comparison is that they have to be the same. So the way we do this is we can do just the value checks, or we can do something smarter, a little bit trickier, is to do the exclusive OR operation. If the two values are different, the exclusive OR is going to be 1, and we want the update of that, so we can just do an exclusive OR with 1. So this will give us this will tell us whether I and j are of the same value. So that's that. One last thing is that we have to have the key to be hashable. So the list here, if we're directly using the cells as the state, we will not be able to hash it. So for that reason, for the state, we actually use a tuple. So the initial state is just convert the cells into a tuple, and we also in the get next we also return the tuple. So that will be a brute force, not brute force, a reasonable solution to this question. Nope. My module is problematic. Oh. So range 0 is problematic. Okay. So let me actually just still have this here. This time, what about this time? This time it works. Okay. So the time complexity for this is order of 8. Basically we create a list array of size 8, and each time here we have 6 fixed constant time operation append with the left and right, so it's about linear with respect to the cells, the length of the cells. So that's let's just call this okay. The loop here we can see it's the minimum between n and the maximum loop size. The loop is going to be upper bounded by 2 to the power of 6, because we have 6 cells that can change values. The total combination is 2 to the power of 6. So this is order of minimum between n and to the power of k minus 2. And this thing will be multiplied by the time complexity for the get next, so it's order of k. And this very last for loop is this thing here. To the power of k minus 2 subtract multiplied by k. K is the get next, and the loop here is in the worst case is just one last step, or one less day compared to a complete day. So we can actually use another set to do the reverse kind of mapping so that we can do the lookup, but that's a lot of code. Anyway, this is a working solution. I think it's going to be okay for interview. The thing that can potentially be improved is if we look at this get next, what it does is to pad 2 zeros on both sides, and then we do element-wise bit operations. So we can if we really convert this into bitmap, it will be achieving bitwise vectorization. Because this thing is essentially a loop, so it's one at a time. If we vectorize it, it will become constant time. So we want to improve this. So how we do this? If we have something smaller, let's say that we have a cell of 4 rows, 1 0 0 1. What we do here is zipping the state with shifted towards right by 2. So it's essentially, having this make a copy of it, state and another state, shifted the first one towards left, shifted the right one towards right, and so let's just call it in bitwise notation, wrong. And if it's go out of the bound, I would just truncate it. This one also got truncated. And I will pad 0 to the place where I don't have enough digits, and I will doing bitwise position-wise, bitwise exclusive operation with a 1, so I can just have a map with all 1s. So I'm doing bitwise exclusive all among these 3 things. So the result will be 0 0 0 0 and 1, that's 1. 0 1, that's 1. 1 and 1, that's 0. So we have 0 and 1. So this is the element-wise, bitwise exclusive among the 2 things. That's those 2 shifted. So this comparing neighborhoods, and mask with a 1 to get the whether the neighbor actually agree with each other or not. And then we want to do one thing, that's to suppress the 2 boundaries. We'll have another mask. So this is mask 1, this is another mask, and doing an AND operation. This will give us the 0 0 0 0. So that's the illustration about how to convert this into a bitwise operation. Let's do that. Okay. So actually we can take advantage, try to use this as a chance to relax this 8, because this 8 is not, it's kind of arbitrary. So bits, it's going to be length of cells. We have 2 masks. Mask 1 is all 1. That's 1 shift towards left by this number of bits, subtracted by 1. Mask 2 is this mask 1, shift towards right by 1, and set the last bit to 0. So that's equivalent of saying just subtract by 1. And then the get state here is going to be doing this. It's going to be exclusive of between 2 things and a mask, the mask 1. So that's the converting this from from the element by element operation into vectorized operations. To able to use this as state, we want to have helper functions that converts the cells and this binary representation. We need the back and forth conversion. So the two cells is to convert the binary representation into the actual cells. So what we do is to enumerate over the bits in the state, and since that we just tested the last bits. If it's 1, we will set the rightmost element to be that number, and then we want to shift the states towards the right by 1. So after this function, we'll be converting the state into the cells. And then we need a helper to convert the cells back to the states. Initialize an empty state. And just gonna, for all the values in the cell, we update the state. That's the formula. The reason being that it's bits -1 minus I is that we're starting with a single bit. The most that we need to shift towards left is going to be number of bits -1. So the I starts 0. So it's going to shift the bits from the single bit position to the leftmost. And when I is incrementing, we're shifting the second bit towards the last to the leftmost. So here, instead of converting this to tuple, we use now a function to do this conversion. And whenever we return a state, we want to return the conversion. So let's see if it works. All right. Yeah. So with this modification, we now have a constant time get next. Not really. It's a vectorized. It's going to be faster than the for loop here, but it's not necessarily truly constant. But it needs a lot of helper to convert back and forth between the array representation for the state and the bitmap representation. And it will also drop the space requirement for the memo. Before it will be k multiplied by the minimum between n and 2 to the power of k minus 2. But now we basically just replace the k by constant. So that's it for today.